the vet's office, and they had a little sheet on their desk showing this. Familiar with a supposed equivalence between people years and dog years? What's the relationship? Okay, multiply by 7, right? Well, this is what they had on their desk. And that's kind of cool. Can I have a copy? And obviously, they've been asked this question a dozen times before because they just reached in a drawer and pulled out a copy right away. So I wasn't the first. But here's that relationship. And what we're going to do is we're going to try and quantify that relationship. First of all, let's actually see if there's a linear relationship amongst these. So we've got that data already in statistic here. How can we determine if there's a linear relationship between these things? There's two things we can do. What did we do the other day? Yeah, we can run a regression and we can just look at the data. All right, we can do a little scatter plot. So if you go underneath data and you do a scatter plot, see we want X is column 1, Y is column 2. Let's do a plot of our data. What do you think? Does it look like there's a linear relationship? Yeah, sure. I mean, they even helpfully put in this line for us. And it's this line that we're looking for. This line is the subject of this section. It's called a regression line. It's a line that fits the data the best in a certain sense. And I'll describe that certain sense for you. But it fits the data in the best way possible if you're trying to minimize something called the sum of squares. All right, so let's actually try and find that equation, and that's going to be our regression. So if we go to analysis, correlation, and regression, of course, if we had gone here in the first place, it would have given us this plot anyways, but I wanted to do things slowly. We've got everything substituted in here. Let's evaluate. So it gives us a lot of numbers, etc. One of the numbers that you should see is something that we worked with in section 10.2, and that's the correlation coefficient. R is 0.9979. Is anyone surprised that that's close to 1? When you take a look back at your graph, and these dots fall pretty tightly around that line. So it's not a big surprise that you're getting a correlation coefficient that's close to 1. Now, the test of whether or not there's a significant linear correlation is, I don't know, is that very significant? Would you reject that there's no correlation, or would you fail to reject that there's no correlation? The default test in these kinds of things is that there's no correlation. So H naught such that rho equals 0 versus HA rho is different than 0. So our p-value for this one is 0.000. I haven't really given you an alpha to work with, but what would you say? Would you reject H naught or accept H naught? Yeah, you'd reject. All right. There's a significant correlation. It's something different than 0. All right. Let's look back at the data here. What we're interested in now in this section is, well, what's the equation of the line? What line summarizes our data? All right, well, let's see. I guess I can get rid of this. Right here. We have y equals b sub 0 plus b sub 1 times x. So what's all that mean? Well, for that, we should probably review a little bit about the equations of lines. Let's look back here for a second. Y equals b sub 0 plus b1 times x. This is a linear equation. It's in what's called slope-intercept form, or y equals mx plus b. And to understand this, maybe we'll go back and take a look at a couple graphs real quick. So a handy form or a handy program to look at graphs with is something called Desmos. That is assuming you don't have a graphing calculator or don't feel like taking yours out. Desmos is everywhere. You don't need to set up an account. You can just click Start Graphing. Let's see. So let's type in an equation y equals 0.5x plus 2. So this is just trying to remind you real quickly about what some of these things mean. Now, the graph touches the y-axis at the point 0, 2. That point is called the y-intercept. So let's see. That is your y-intercept. And the other number here, m, is your slope. And I'm sorry that looks like a really rotten m, but it is an m. M is your slope. And what the slope is it's a ratio of two things. It's a ratio of the rise over the run. So coming back here, slope, m is the rise over the run. And you can see what's happening in this particular case. The run is the horizontal distance. So moving from -4 to 0, you've got a distance of 4. And then moving up from 0 to 2, you moved a distance of 2. So overall, the slope is 1/2. So this number here is your slope. So you got the slope and the intercept. If this were an algebra class, I'd talk to you a little bit more about it. But this is called the slope-intercept form of the line. That's the form that you're going to get your equations in, more or less, out of StatDisk or any package that you choose to use, even your graphing calculator. They're going to give you something in that form. So what was the answer in this particular case? Well, in this particular case, the y-intercept is your b sub 0. That's where the graph touches the x-axis. So y equals 11.62 plus the slope. The slope is how your graph is changing. It's 4.62 times x. X is your independent variable. That's your age in people years. And then what we'll get in y is your age in dog years. So your equation looks like this. I tend to prefer to write it like this, 4.62x plus 11.62 like that. That's just habit. Doesn't really make much difference. But looking back at this, we can now say a little bit more about what this is. Keeping in mind that your x variable is age in people years, and this is your age in dog years. Let's see what this regression line is telling us about that relationship. What the slope is saying is that for every 1 people year, how much does a dog age? So for every additional person year, a dog ages another 4.62 years in dog years. So a little bit different than the 7 that we're used to. But then again, if you wanted to kind of be literal about this, when dogs pop out, they're already almost a teenager. They're a preteen here, right? They're almost 12 years old. If this line could be taken literally. Now, this does kind of highlight something that Chris noted the other day, and that is you have to be careful making predictions outside of your data. That is, our data runs from 1 to 18. It's a little dicey once you move outside that range, particular, it doesn't really make sense that, you know, at day 0, a dog is already equivalent to almost 12 years old. But what I'm more concerned about is you understanding the interpretation of the slope. Each additional person year adds 4.62 to the equivalent dog years. That's what I want you to be able to get out of this. So, how are we looking on that first one? Looking okay here? By the way, just to give you a perspective of how easy StatDisk makes things for you, let's just take a look at just the calculation for R. So if you wanted to calculate R, and you had some data here, and don't copy this down. I'm not really trying to teach you how to calculate this by hand, but I just want you to appreciate how nice some of this technology is making things for you. You'd have to come up with several things. You'd have to take your X and Y data, sum it all up. You'd have to square these things, so 12 squared is 144, 7 squared 140 or 49, etc., and then take the product of these things, and then get all these sums. So fair amount of work there. Hit the freeze button. No. SSX, sum of squares about the x's, sum of squares about the y's. Calculate these three totals, and then plug it in here to finally get your coefficient of R. It's a lot. And we have to do a little bit more work to find B sub 0 and B sub 1. So this technology is really, really helping us out considerably. It's a good thing that we have it available to us. I'm much happier doing it by computer as opposed to by hand. All right, let's try another one. I think it's problem number 18 in the book, but let me just double check. Sure, problem number 18. All right, so we want to decide if the opening bid is a good predictor of the winning bid. So this would be our X, and this would be your Y. We're going to put these things in. And first of all, look and see whether or not looks like there's a linear relationship, and then try and quantify that relationship. So let's go back to StatDisk, and I can shut this down. Let's clear out this data and enter some new data. So for the X's, I'll have 1500, 500, 500 again, 400, and 300. Moving over to the Y's, the winning bid, 650, 175, 125, 275, and 125. Let's just go to analysis, kind of cut out that middleman of the scatter plot, because we can get a scatter plot from our correlation. If we click evaluate, then right underneath, after you click evaluate, we can click scatter plot. does there look like there's a linear correlation? Yeah, ish. A lot of that linear correlation, I think, is probably because of this one point here, way out here at 1500. So without that, if you're just looking at these four values, then it doesn't look like there's much of a correlation. In fact, maybe what we'll do is we'll rerun it after we delete that value. But as it is, okay, it looks like there's a linear correlation. So let me go back to our results. Is that a significant correlation? Well, here's our correlation coefficient, and the p-value for that test is 0.015. So does it look like there's a significantly non-zero linear correlation? Would we reject H naught such that rho equals 0? Don't make Chris do all the work. We're going to... So in problem number 18 here, we want to look at whether or not there's a significant non-zero correlation. So we're doing this test. So this says there's no linear correlation. And this says that there is a linear correlation, although we don't know which direction it is, but there's a significant nonlinear correlation, or excuse me, significant linear correlation. You're going to reject H naught at all but the most extreme values of alpha. Our p-value is 0.01537. So unless you decide for whatever reason that your value of alpha has to be less than that, then you're going to reject. There is a significant linear correlation. In fact, our linear correlation coefficient is pretty high. It's 0.944. So that's pretty good. That one's up here. We'll see what else that we can get from this. One of the other things we should get is the equation of the line. So the equation here, in fact, why don't you see if you can't put it together? Here's the relevant information. Write down what the equation is. Are those numbers too small to read from the back? David, can you read those in back? Okay. You getting Devon values? Did I? 1, 2, 3, 4, 5. No, I didn't take out the row yet. Okay. Let's take a look back here at the data then. No status. 56. Okay. Thank you. 125. 275. Okay. Let's see if the CFR is matched now. Let's close this out. Okay. All right, so it does make a bit of a difference in our line. Let me cross out that old one. Thanks for spotting that. So the equation of the line you should be getting looks like this. 0.4291x minus 4.62 for y. That's a good question. In this case, let's see. I think the author says to use one more digit than is there in the original data. So, I guess I've gone a little bit beyond that. That's all right. I'd rather have more than less. I'll try and be specific about what I'd want. If you're following along with the author's recommendations, then this would be, say, y hat is 0.4x minus 4.6. That seems a little coarse. I'd be happier with 2 or even 3. But where it makes a difference to me, I'll try and be specific on the test. Round your answers to a set number of digits. Yeah, I think this one in particular, the graph of this is going to look a fair amount different than the graph of this one. So I'd at least give 2 digits. 2 digits beyond what the data gives. Now I keep on calling this y hat. This is yet another statistic. So let's go back and revisit a few of these things. Any questions on what we've got here? Tell you what, before we revisit some stuff, let's look at the equation. What's the slope of this equation? Oh, do you have a question? Yes. Yeah, I think the output had a negative here. Yes. So the y-intercept is negative. Let's see if we can interpret these in words. So this is X is the price of the opening bid. And Y is the price of the winning bid. Now maybe I should be looking at this one up here because that's a little bit more accurate of a representation. But the slope and response are still going to be the same. Let's see if we can't put that into words. For every additional dollar that you have here as part of the price of the opening bid, what's the effect on the winning bid? For every extra dollar here, what's the response here? Increased by how much? Yeah, about 43 cents, the slope, right? So for each additional $1 increase in the opening bid, there is an increase of 43 cents in the winning bid. Let me be very specific about this. This is what I want you to know. We're not doing a lot of the calculations by hand that we used to. So we're going to put our efforts into interpreting and understanding this. You need to be able to explain these results to somebody who doesn't have a statistics background. They're not going to say, oh, gee, you rejected H naught, so there's a significant linear correlation. Great, what's that mean? What's this line telling me? So your job as a statistician is to try and interpret this and bring this down to somebody's level who maybe is educated and stuff like that, but doesn't have the stat background that you do. Now there's another thing that's part of the output here that we want to discuss, and that is R squared. This is your coefficient of determination. And you might notice something about R and R squared. First of all, does anyone remember the name of R? What was R? The actual statistic R, which estimates rho. Linear correlation coefficient. But these two have the relationship that you would expect. That is, if you square this one, you get this one. If you take the square root of this one, you get plus or minus this one. And you have to choose the plus or minus depending on if it's a positive or negative relationship. But let's take a look at our current value of R of 0.9449. And let's square that. See what we get. Is it 9468?
Yeah, it changed when you...
Oh, okay. All right, 9468, thank you. 9468. 0.9468. If I hit the square key on my calculator, I get about 0.8964. Let's compare that to the output from StatDisk. So here's our linear correlation coefficient, 0.96 or 9468, etc. When we square that, we should get R squared. Coefficient of determination, R squared. There we go, 0.8966. So there's a nice relationship between these two things. We can see that. But what does that coefficient of determination tell you? What does it mean? What is it saying? So let's discuss that a little bit. And let's look back at our scatter plot for a second. Now think about just the y variables in this scatter plot. We've got a y variable here, here, down to here, a couple down here, etc. So there's a fair amount of variation in the y variables. So what the coefficient of determination is explaining is how much of that variability is explained by knowing the x value. That is the independent value. So let's write down a definition for ourselves, or at least a nice, good understanding. R squared represents the proportion of variation in y, which is your dependent variable. Sure, thank you. R squared represents the proportion of variation in y, your dependent variable, that is explained by knowing the value of x, which is your independent variable. It's a measure of how good your line is doing in terms of explaining the data. Now you might remember that R itself is between 0, it's going to be -1 and 1. R squared, if you were to square this, you would find that R squared is between 0 and 1. So if you have an R squared of 1, then that means your data is perfect. That is, knowing X tells you exactly what Y is. If you have an R squared of 0, knowing what X is tells you nothing about Y. And of course, there's every possibility in between. So an R squared of 0.9 is really good. That's telling you a lot about your data. Not quite this one I wanted you to do. A number of years ago, because gas was so expensive at the time, and for a lot of reasons, I bought a hybrid to drive around in. And I kept track of my mileage. I'm a statistician. It's just kind of a thing I do. I kept track of gas mileage. And I noticed something. I noticed some seasonal variation, etc. But I also did get a nice relationship if I were to plot temperature versus gas mileage. Now, what kind of things do you think can affect your gas mileage other than just temperature? What are the things that would affect how many MPGs you get? Yeah, driving habits, sure. Type of fuel, yeah, because there's a different blend in summer than there is in winter. Yeah. Let's see, how much traffic you run into, if your car is in tune, if your tires have the right pressure, etc. So can we agree that there's a lot of things that affect your gas mileage? When I ran a regression of temperature versus gas mileage, MPG, so temperature versus MPG, I got a value of R squared, and this is going off of memory, somewhere around 0.64 or 64%. Well, what's that telling you? What's that telling me? It's telling me that 64% of the variability in gas mileage, or MPG, is explained by knowing the temperature. That was pretty remarkable. Of all the things that could affect your gas mileage, just knowing how warm it was outside explained 64% of the variation. So that was pretty substantial, I thought. And even the value for temperature, I went on the internet and I found the average monthly temperature, or the average temperature in the weeks of, between filling up tanks. So that temperature really wasn't all that accurate. If I was being more accurate about it, I could probably get that value of R squared up even higher. This is just using a very loose measure of the temperature there. Are you comfortable with what R squared is representing here for us? That's a correlation, although in this particular case you can do a causation. It takes your engine longer to warm up. In the case of a hybrid, you're not going to be running on the electric power until the engine warms up, etc. So in this case, you can draw a line between temperature and MPG in terms of a cause and effect. So it's more than just a correlation. Yeah, it's a great question. We're going to spend some time on correlation after this section. We'll do a whole thing on correlation. Now there's other types of regression that you can run as well. You don't have to always fit a linear regression, although quite often that's what we're going to work on. And in this course, that's really all we're going to work on is linear regressions. That is data that represents a line. But quite easily, especially with statistical packages, you can fit things that are quadratic regressions, things that are shaped like a parabola. Cubic regressions. Things that are periodic would be like a sine regression. And this is what I could do for instance, for the MPGs that I was getting. Seems to go up and down with the season. If you look at this graph here, then its variation reflects the variation in the seasons. Power regressions, logistic regressions, which aren't even here, logarithmic regressions, a lot of different shapes that we can work with. So when you take some more stat classes, you can pick those kinds of things up. Let's do one more from StatDisk. Let's do problem number 29, so one of your homework problems. In Appendix B, use the paired data consisting of IQ score and brain volume. Find the best predicted IQ score for someone with a brain volume of 1,000 cubic centimeters. So let's load a data set 6, and see if we can make some predictions. We're going to look at the relationship between brain volume and IQ score. And then we're going to go and use our data set, or our regression line to make a prediction. So let's go to data sets, 12th edition, and it's data set 6, IQ and brain size. IQ, yeah, 4 and 5. Okay, thank you. Go down to analysis, correlation, and regression. This time we can choose 4 is your X variable. That's your independent variable. And we're hoping that, actually, you know what? I would think of 5 as the independent variable. The volume predicts the IQ. At least that's the way I see it. Let's see. Let's double check what the book has here. Find the best predicted IQ score for someone with a brain volume. Yeah, so they're saying that the volume predicts the IQ. I agree with that. We'll test this at the 5% significance level. Let's do a quick scatter plot just to see what the data looks like. Wow, that's all over the map. Does it look like there's a linear relationship between, brain volume and IQ score? Not really. Now, just kind of a heads up here. No matter what happens, your stat package is always going to fit a regression line. It's always going to come up with this equation here that shows you the slope of a line someplace. But is it a meaningful slope? I mean, let's find out. So, problem number 29. Let's take a quick look at the hypothesis that the slope is essentially 0. There's no slope to the relationship versus, yeah, there's some significant slope to this relationship. Now StatDisk gives us the means to test that. So I'll close out the scatter plot and look at R, the correlation coefficient. R in this case is negative 0.0634, we'll call it. The p-value for this test, so the p-value is 0.790, 0.7906. So what's that telling me about the test of whether or not this is zero? Can I reject H naught so that there's no linear relationship, or excuse me, can I reject H naught so that the relationship, the linear relationship here is essentially zero? Reject or fail to reject? Yeah, fail to reject. Are we close to rejecting? No, no. This is pretty far away from rejecting that hypothesis. So that's not really a surprise. In fact, if you look at this correlation, yeah, all right, there is a slight negative slope to that line, but it itself is pretty close to zero. It's not close to 1 or negative 1. So not a big surprise on that one. Nonetheless, you can still go through the calculations. The calculations say, all right, well, y sub 0 or y hat is, let's see here, we got to come up with this equation of the regression line. Negative 0.0067 x plus 108.54. There's actually a part of this that's it's counterintuitive, at least what I would think. I don't know. What relationship do you think you would expect? Bigger volume, higher IQ? Okay, that's not what we're seeing, is it? If you look at the slope of this line, as volume increases, brain size decreases because the slope of the line is negative. So it doesn't really make much sense in that respect. Let's finish up the problem that they asked. They asked us to make a prediction as to what the IQ would be for somebody with a brain volume of 1,000 cubic centimeters. So let's find the value of y hat. Negative 0.0067 times 1,000 plus 108.54. So that's going to be negative 6.7 plus 108.54. So what? 101.84. So that's your predicted value. Okay? Now, should we be using this line? Not really. Not really, because this slope really wasn't significantly different than zero. We shouldn't be using it to make predictions. But we followed through with what the problem asked us to do anyways, just for the practice. One thing that I'll be asking you to do soon enough is make predictions using your regression equation. So even though we shouldn't have been using it, are you comfortable with our calculation there and what to do to make a prediction? I've been using y hat often enough, and let me add y hat to our list of statistics. Yes, sir. Oh, it's the book. The book asks you to make a prediction for the brain volume or the IQ when the brain volume was 1,000. So, yeah, that was supplied. That was problem 29.
Mine just says refer to data set 6 in Appendix B and use the paired data consisting of rank value and IQ score.
Okay. Not sure why it's not there, but in the book it says 1,000. Okay. So let's revisit some of our old statistics and parameters. And we're going to add a new one to this. So for the mean, the statistic was x bar. The parameter was mu. For the standard deviation, what was the statistic in the parameter? S and sigma. We also had population proportion. P hat and P. Then we had the linear correlation, R and rho. And I really regret that they've used P and rho like this. And then our linear regression. So it's going to be y hat equals b1x plus b sub 0. And the linear regression is capital Y equals beta 1x plus beta 0. So what we're hoping is that this linear regression is a good estimate of the population parameter. We don't know, but we're hoping that that's the case. Now, one thing that's hidden for us quite deeply is what motivated this discussion and how this came about. I believe the original person who came up with this method was a guy by the name of Carl Friedrich Gauss, and he did it to improve his astronomical observations. The regression line comes about from what's called the method of least squares. And what you're essentially trying to do is minimize the square of this distance, the distance between your line and your observation. So this is your observed regression line, y equals b1x plus b sub 0. And you're trying to make the distance between this line and your data small in the sense that you want to minimize the square of this distance. That's why they have these squares here. That's the area. And the line that we're using does that the best, as it minimizes the sum of these squared errors. So, hence the name that this is a least squares regression. No, not in this course. No, we're not. The only one we're going to work on is the linear ones. Yeah, I mean it's not that hard, but you know there's a lot in this course already, so you know it actually wouldn't be that hard. Let me take a quick look at StatDisk. If data analysis, correlation, regression. Yeah, I think this is set up for linear regression. Here, multiple regression would allow essentially a linear regression with a lot of different predictors, a lot of different independent variables, and it's not that bad. Let's just do a few here. Let's see. So we'll do IQ, volume, and height, weight, dependent variable. One column, pair, IQ. So we're going to use IQ as the dependent variable, and let's see. We didn't do much better. If you take a look at our value of R and R squared, you're explaining less than 1% of the variation in volume by knowing something about, or so did we do volume? No, we're explaining 1%, less than 1% of the variation in IQ by knowing something about the volume and the weight. So it's not really significant. But what I'm saying is you can build other models. And a multiple regression is a very, very common thing to do in statistical analysis. Try and find what variables actually influence this. Okay. Keep in mind that later today you're going to have to do your own in-class regression assignment. So before I end things, are you comfortable with regressions? Finding them, interpreting them, making predictions. Okay. All right, for homework, try 1 through 27.